Hi guys, this is A2 Chemistry, Analytical Chemistry, and we are doing Proton or H1 NMR. Question 7. The combination of mass spectroscopy and NMR spectroscopy provides a powerful method of analysis for organic compounds. The mass spectrum of a compound G contains M and M plus 1 peaks in the ratio of their heights of 74 is to 2.5. Use these data to calculate the number of carbon atoms present in G and show your working. So the formula for the calculation of the number of carbon atoms is equal to 100 upon 1.1 multiplied by the heights of M plus 1 peak upon the height of the M peak. So substituting these values in the formula, this would give us 100 upon 1.1 into 2.5 upon 74, which would give us a value of 3.07, which is almost equal to 3 since the number of carbon atoms have to be in whole numbers. So we end up with 3 carbon atoms being present in the given compound. The NMR spectrum of compound G is shown. Use the data booklet and your knowledge of NMR spectroscopy to identify the type of protons responsible for each of these three absorptions. So, the first peak on the right is split into three. That means it is present next to a CH2 group. The next peak from 2 to 3 is split into 4. That means it is present next to a CH3 group. That means a CH3 and a CH2 group are present next to each other. So the second peak, because of its chemical shift range between 2 and 3, also shows that it is present next to a C double bond O group. So we've identified this much part of the structure. And finally, the singlet close to 12 definitely corresponds to the peak for a carboxylic acid, because a carboxylic acid has a singlet peak in the range of 9 to 13, and it is the only peak that has a chemical shift value in that range. The other being aldehyde with the singlet peak lying between 9.3 and 10.5, and this peak present on our spectrum goes beyond 10.5. So it has to be a carboxylic acid. So the carboxylic acid having three carbon atoms on it is propanoic acid. So this NMR spectrum is of propanoic acid. Okay. So now we need to identify the type of proton. So for the peak at 1.1, it is a CH3 group next to an alkyl group. For the one at 2.2, it is a CH2 group next to a C double bond O. And for 11.8, it is a C double OH group. Next, the addition of D2O causes one of these absorptions to disappear. Explain why this happens and state which absorption is affected. So the singlet at delta equals 11.8 ppm disappears due to proton exchange. So the proton present in COOH is a labile proton, and we give an equation for this proton exchange taking place. That would be R COOH plus D2O, giving us R COOD plus HOD. So the proton in the COOH group is substituted by a deuterium atom, and therefore its peak disappears. Draw the structural formula of G. So the structural formula of G is CH3 present next to a CH2 group, present next to a C double bond O group, which is part of a carboxylic group. So CH3, CH2, C double OH. Several structural isomers of G exist. Draw the structural formula of an isomer of G with only two absorptions in its NMR spectrum. So the structural isomers, or rather the functional isomers for carboxylic acids are esters. So the C double bond O single bond O group would be present, And since it has two absorptions, we would place a CH3 group next to oxygen and a CH3 group next to C double bond O, completing the requirement. So this ester is methyl ethanoate. And use the data book to suggest where these absorptions would occur. So we would have a CH3 next to oxygen being present in the range of 3.2 to 4.0, and the CHC next to C double bond O in the range of 2.2 to 3.0. So we put this down as the first peak would be for a CH3 next to CO in the chemical shift range of 2.2 to 3.0 ppm, and the peak for CH3 next to oxygen in the chemical shift range of 3.2 to 4.0 ppm. Question 8. T is a saturated alcohol. It was analyzed by mass spectroscopy and NMR spectroscopy. In the mass spectrum, the molecular ion peak M was at an ME value of 74, and the ratio of the heights of the M and M plus 1 peaks was 20.4 and 0.9. So the MR of this compound is 74, and the number of carbon atoms present is given by 100 upon 1.1 into 0.9 upon 20.4. So this would give us a total number of almost 4, because we round the value to the nearest whole number, 4 carbon atoms. So a total of 4 carbon atoms are present in our saturated alcohol, which means there are only single bonds present. And the number of environments seen are 4. The first environment is a doublet because it is next to a single proton. The second environment is a multiplet because it is between multiple protons. The third environment is a singlet, and since it is an alcohol, this is the peak for the OH group. And the fourth environment is a doublet, which is also next to a single proton. So in total, there are 4 absorptions present in our saturated alcohol and 3 environments corresponding to the 4 carbon atoms, which also means 2 of the carbon atoms are present on the same carbon atom having the same environment for each. So we can actually conclude that there are 2 CH3 groups present on a carbon atom with a single hydrogen on it, because we have a doublet peak. So the first peak would be for two CH3 groups, and the multiplet would correspond to the CH group because it is present next to two CH3 groups, and a CH2 group because we've got another doublet in our NMR spectrum corresponding to another hydrogen environment, and we've got a singlet for the OH group present. So the second doublet in our NMR spectrum would be because of the CH2 group present next to the alcohol functional group. So in this way, we have identified the alcohol responsible for the given NMR spectrum. Use the information and your answer above to deduce the structure of T. So we've already identified the structure of T. T, CH3, CH, another CH3, a CH2, and an OH group. So this alcohol is 2-methyl propanol. Describe and explain which types of protons is responsible for each of the absorptions. So absorptions that we have been given are between 0.9 and 1.0, or rather we put it at 0.9 ppm. The absorption is due to two CH3 groups next to an R group. Then the absorption at 1.8 ppm is due to a CH group present between alkyl groups. So that is the peak for the CH group, the multiplet. So we can also write that the first peak is a doublet, the second peak is a multiplet, the third peak at 3.4 ppm is due to the OH group of an alcohol, and it is a singlet because it is a functional group peak, and the peak at this peak is at 3.4. So the peak for the alcohol is not at 3.4, that is at around 2.5. So let's correct the mistake. This peak is at 2.5 ppm for the alcohol. So the peak at 3.4 is due to a CH2 group present next to an oxygen atom, and this peak is also a doublet because it is present in an environment next to which there is a single proton present. The absorption at 1.8 ppm is a multiplet and that at 2.5 is a singlet. State and explain the splitting patterns of the absorptions at 0.9 and 3.4. Both are doublets due to them being present in an environment in which a single proton is present adjacent to them. Describe and explain how the NMR spectrum of T dissolved and D2O would differ from the one shown. So we have an OH group present. So the singlet peak at delta equals 2.5 ppm would disappear since it contains a labile proton which undergoes proton exchange. And we conclude this explanation or description with an equation. So it would be ROH on reaction with D2O producing ROD and HOD, and due to this proton exchange the peak disappears. Question 9. The proton NMR spectrum of a sample of 1-phenylethanol shows 4 peaks, a multiplet for the CCH5 proton, and 3 other peaks as shown in the table. When the sample is shaken with D2O and the proton NMR spectrum recorded, fewer peaks are seen. Complete the table for the proton NMR spectrum of 1-phenyl ethanol. The formula is given and use of data booklet will be helpful. So if we make this formula like this, we've got a benzene ring attached to a CH group attached to an OH group on one side and a CH3 group on the other. This would give us a much more clearer picture of which peak corresponds to which environment. So we have benzene ring. So the peak for the benzene ring lies in the range of 6 to 9 ppm. We have an alcohol group which lies in the range of 0.5 till 6.0 ppm. We've got a CH next to a CH3, next to a aromatic ring and next to OH. The range for the CH that would be relevant would be the next to oxygen, which would be 3.2 to 4.0, and the peak for the CH3 group next to an alkyl group would be 0.9 to 1.7. So now let's see which peak corresponds to which range. So the first one is 1.4. Now 1.4 can lie in the alcohol range as well as the CH3 next to alkyl. So there are two possibilities for 1.4. So moving on, we've got a 2.7. So the 2.7 can only lie in the range of 0.5 to 6.0. Therefore, it is the peak responsible for the alcohol group. So group responsible for this peak would be ROH, and the number of H1 atoms responsible for the peak would be 1 because there is a single hydrogen atom in the OH group. So the splitting pattern for the OH group will always be a singlet, and result of checking with D2O, the peak would disappear. So we've identified the OH group, which means the peak at 1.4, if it is no longer the peak for the OH group, it is the peak for the CH3 group next to an alkyl group. This would contain 3 protons, and the splitting pattern for this peak, because it is present next to a CH group, would be a doublet. And result on checking with D2 is that the peak remains because it does not contain any labile protons. And for the peak at 4.0, it is the peak for the CH group next to oxygen. Now the CH group contains a single proton, and the splitting pattern, because it is present next to a CHC group, would be a quartet. And since it does not contain any labile protons present, this peak would also remain. And the last peak between 7.2 to 7.4 ppm is for the benzene ring, which contains 5 protons, and its peak would be having a splitting pattern as a multiplet. And this peak also does not contain any labile protons, so this peak would also remain on shaking with D2O. At this part of the table has already been filled. Question 10. A sample of benzocaine shown below was analyzed by proton NMR and carbon-13 NMR spectroscopy. Benzocaine was dissolved in CdCl3 and the proton NMR spectrum of this solution was recorded. So we've got 5 different peaks in the NMR spectrum. The peak at 0 corresponds to the reference compound TMS or tetramethylsilane. So the peak from 1 and 1.5, between 1 and 1.5 ppm, is next to a CH2 group. That means it is in the alkyl range. So this has to be the CH3 group present in benzocaine. Then we have a peak between 3 and 4, which would be an alkyl group next to oxygen. So that would correspond to the CH2 group present. Since it is next to a CH3, so it will split into 4. Then we have a singlet in the range of 5 and 6, close to 5.5. That would be due to the functional group amine. And then we've got a multiplet in the range of 7 and 7.5 that corresponds to the aromatic ring, because the aromatic ring has a multiplet and it corresponds to the four protons present in that aromatic ring because we have two substitutions present on it. So we have identified which peak corresponds to which part of our benzocaine molecule. Suggest why CdCl3 and not CHCl3 is used as the solvent when obtaining a proton NMR spectrum. CdCl3 will not produce any peak, while CHCl3 would produce a singlet which would interfere with the NMR spectrum of benzocaine. Use the data booklet and the spectrum above to complete the table for the proton NMR spectrum of benzocaine. The actual chemical shifts of the four absorptions have been added. So we have already identified which peak corresponds to which environment. So we just need to put down the exact peaks for the relevant chemical shift value. So groups responsible for the peaks. So at 1.2, it is a CH3 group next to an alkyl group. Number of H1 atoms responsible. So there are three protons present in CH3, and the splitting pattern shown is a triplet. Next, we have the peak at 3.5. The peak at 3.5 is a CH2 group present next to oxygen. CH2 group contains two protons, and the splitting pattern shown is a quartet. Next, we have the peak at 5.5. This peak is for the NH2 group present next to the benzene ring or the aromatic ring, and NH2 contains two protons, and since it is a functional group peak, it would be a singlet. And lastly, we have the multiplet at 7.1 to 7.4. This is due to the C6H4 part of the molecule, and C6H4 contains four protons, and the peak would be a multiplet as shown in the NMR spectrum. Explain the splitting pattern for the absorption at 1.2. So the absorption at 1.2 is a triplet due to the presence of two protons in the adjacent chemical environment. The proton NMR spectrum of benzocaine dissolved in D2O was recorded. Suggest how this spectrum would differ from the spectrum in D2. Explain your answer. So the singlet at delta equals 5.5 ppm would disappear due to proton exchange since it contains labile protons, and the equation for this would be RNH2 plus D2O giving us RNHD plus HOD. So the two protons attached to the nitrogen atom are labile protons. Even if one of them is substituted or exchanged for a deuterium atom, the peak at 5.5 parts per million chemical shift value would disappear. Question 11. A sample of calcitriol is treated with an excess of hot concentrated acidified potassium manganate 7. There are three different carbon containing products of this reaction. One of these three products is X shown. Okay. Predict the number of peaks for this compound would show in its proton NMR spectrum. So this carbon will not show any peak, this will not show any peak, this will not show any peak, this will not show any peak. This is a CH2 group, this is also a CH2 group. Now, since we've got two positions where protons are present, but both of them are present between two C double bond O groups, that means both of them will have the same environment. Therefore, predict the number of peaks, a single peak, because they have the same environment, so only a single peak would be observed. For each of the peaks in the proton NMR spectrum you have identified, give the expected splitting pattern, explain your reasoning. So the peak would be a singlet as there are no protons present in the adjacent chemical environments. So since there are no chemicals present, no protons present in the adjacent chemical environments, the splitting pattern would be a singlet. And since both the CH2 groups are present in the same environment, there would only be a single peak, which would be a singlet in the NMR spectrum of